This is a tutorial for ME 555, spring of 2013. Today, we are going to discuss different aspects of lithium-ion battery thermal modeling. I hope you enjoy this material. For convenience, we are going to divide this tutorial into three main areas. First, we will find an explanation to why are the thermodynamics of a lithium-ion battery important. Then, we will look at different types of models. And finally, we will conclude with a summary of our findings. So let's get started. In the first part of this tutorial, we will focus on how a lithium-ion battery works and how its performance and life is temperature dependent. We will do this by analyzing battery performance at both low and high temperatures. To conclude the first section, we will look at the case of thermal runaway. First of all, let's recognize that the lithium-ion battery is the power source for a wide variety of devices, including modern electric vehicles. As an interesting fact, the battery pack of a Tesla Roadster contains more than 6,800 lithium-ion battery cells like the one on your screen. Let's begin by taking a closer look at the inside of an 18650 lithium-ion battery. The electric current reaches the cell through the current collectors. In the case of lithium-ion batteries, these are made out of copper in the negative electrode or anode and aluminum in the positive electrode or cathode. The cathode consists of a very pure metal oxide. Some of the most common chemistries for cathode materials are lithium cobalt oxide, lithium manganese oxide, and lithium iron phosphate. It is important to note that lithium-ion batteries are called by the chemistries of the cathode materials. On the opposite side, the anode is made out of graphite or lithium titanate or silicon-based materials. The battery cell is submerged into an electrolyte, a material that works as a transport medium, allowing lithium ions to diffuse freely from one electrode to the other. This electrolyte is commonly a lithium salt in a carbonate solvent, like lithium hexafluorophosphate. To prevent the cell from a short circuit, the separator is placed in between the two electrodes. The microporosity property of the separator makes it permeable for the lithium ions to flow freely from one electrode into the other. Now, let's see what happens inside the battery when it is being discharged. The positively charged lithium ions diffuse via the electrolyte from the anode through the separator and into the positive electrode where they are inserted and stored. The reverse process happens when the battery is being charged. The equations on each side of this slide summarize the reaction for both charging and discharging of a lithium-ion cell. Please note that discharge happens to the right and charge to the left. Now that we have analyzed how a lithium-ion battery works, let's take a look at the way in which temperature affects its performance. Like humans, batteries have a narrow window for optimal operation. Deviating from this temperature frame impacts battery performance and/or life. As you may see on your screen, the temperature range of a lithium-ion battery is from 0 to 100 degrees Celsius and from 2 to 4 volts. As your intuition tells you, higher temperatures initially speed up battery reactions and reduce internal resistances. But after a period of time, as heat accumulates and temperature rises, the battery experiences thermal stresses and some components of the battery may start to decompose, leading to thermal runaway. Likewise, lithium-ion batteries are not very efficient at drastically low temperatures, especially during charging. As shown in this figure, lithium-ion cells start losing some of its capacity right at freezing point. As temperatures drop even lower, the diffusion of lithium ions is so slow that lithium plating may happen. Please note that this is also dependent on the battery's history, state of charge, and chemistry. Please spend some time looking at the effects of different temperature and voltage conditions on a lithium-ion cell. For example, you may note that the current collectors are the first component of the battery to start decomposing at relatively high temperature conditions. Similarly, you may see that even though thermal runaway happens at temperatures beyond 300 Celsius, other components of the battery start to decompose at much lower temperatures, such as the separator, the cathode material, and the electrolyte. High temperature conditions usually take most of the attention, time, and funding in lithium-ion battery thermal research. However, very interesting things happen in a lithium-ion battery at low temperatures, especially during charging. This is particularly true in towns like State College, where the winter spans for longer periods of time. After we spend some time looking at the visible effects of temperature over a spectrum of operating voltages, let's take a closer and much more detailed look at the effects of low temperatures on lithium-ion cells. As temperature drops down, batteries may experience the following phenomena. First, reduced ionic conductivity of the electrolyte and solid electrolyte interface. Second, limited diffusivity of lithium ions in the electrodes. Third, high polarization of the graphite anode. Fourth, increased charge transfer resistance or a decrease in kinetic reactions on the electrolyte and electrode interfaces. These events manifest as charge transfer resistance increases significantly below -10 degrees Celsius. Lithium-ion batteries in this charged state suffer higher polarization. Lithium-ion batteries at -40 degrees Celsius have 5% of energy density and 1.25% of power density of those batteries at 20 degrees Celsius. At low temperatures, lithium-ion batteries cannot be fully charged. Let's move forward and take a look at other effects. To wrap up this first section, let's take a look at thermal runaway, a popular term in lithium-ion battery research. Thermal runaway refers to a situation in which temperature increases steadily, often leading to destructive results. In lithium-ion batteries, if the rate of heat transfer is less than the rate of heat generation, the steady increase in temperature may lead to thermal runaway. Batteries may go into thermal runaway when subject to one or a combination of the following abuses. We are looking at the left column of your screen. Overcharging, overdischarging, high C rates, external heating, and nail penetration. Although all of these conditions lead to thermal runaway, the mechanisms that initiate may be different. The two most common cases are lithium plating and internal short circuit. Thermal runaway involves different stages. We are now on the third column on your screen. At temperatures as low as 80 degrees Celsius, the SEI layer starts to break down. As temperature continues to climb and reach 110 degrees Celsius, the electrolyte decomposes. Further, At 135 degrees Celsius, the separator melts. And at even higher temperature, the cathode breaks down. As heat exceeds the dissipation rate, thermal runaway may happen, and it is characterized by venting, flames, cell disassembly, smoke, and leak. Once thermal runaway is initiated in a single cell, it propagates fast into adjacent cells in a battery pack. Now that we understand how a lithium-ion battery works and the effect of temperature in performance, we may want to take a look at different types of models. In this way, we can estimate battery temperature profiles and battery performance. As seen in a previous tutorial, there exist different types of battery models, each one associated with a different level of accuracy, complexity, and computational cost. Today, we are going to add one more level of complexity by incorporating thermal effects. Battery performance is highly dependent on temperature conditions. The main goals of thermal modeling are: first, to avoid exceeding the rate of heat dissipation in a battery cell, thus avoid thermal runaway. Second, determine the effect of battery parameters on temperature dynamics. This is mostly true for battery design. And third, although not written in this slide, but we've been talking about it throughout this tutorial, another goal of thermal modeling is to estimate the performance of a battery cell incorporating temperature effects. Modeling the rate of heat generation and dissipation in a cell is needed to perform accurate thermal management in battery packs. There are multiple types of thermal models for different applications and levels of accuracy. The main categories of thermal models or battery models are experimental models, lump parameter models, and multi-scale, multidimensional, and multiphysics models. Within this category, we have thermal electrochemical coupled models, which use single particle models, pseudo 2D and 3D models. The first type of model that we are going to look at is the empirical model. The diagram on the right-hand corner displays the most simple equivalent circuit model. However, more complex model may include additional RC circuits in parallel, describing different dynamics in a battery system. Empirical models rely on previous experimental data to estimate the behavior of battery cells at different operating conditions. Some of the advantages associated with this type of models are computational easiness and low mathematical complexity. However, the disadvantages are that they do not incorporate physicochemical properties, that they have poor prediction at different operating conditions other than those collected during experimentation, and that they are useless for battery design. Nonetheless, it is important to note that empirical models are widely used in the design of battery management systems. The energy balance equation is a powerful tool. It allows us to link temperature effects into the electrochemistry equations, therefore increasing the accuracy of our models. Using an average heat capacity and neglecting enthalpy of mixing and phase change, all safe assumptions for an 18650 lithium-ion battery cell, the energy balance equation reduces to the expression on your screen. Please spend some time getting acquainted with this expression, as it is perhaps the single most important thing in this tutorial. Let's look at each of the terms in this equation. On the left-hand side of the equal sign, we have the time variation of enthalpy, where MCP is the thermal mass of the battery, and T dot is the time rate of change of temperature. On the right hand side, we have the convection heat transfer rate, where H is the convection heat transfer coefficient, which is a function of Reynolds number, which is a function of flow and geometry, and Prandtl number, which is a property of the fluid in which the battery is submerged. The second and third terms on the right hand side are the irreversible heat generation and the reversible heat generation terms. The irreversible heat generation is caused by ohmic heat losses, and it originates by current rate, limited conductivity, and contact resistance between the current collectors and the electrodes. This term is proportional to I squared R. The reversible heat generation is also known as the entropic heat, and it might be negative or positive depending on the level of disorder of the system. We are now ready to give a step up in complexity and move to multiphysics models. Multiphysics models couple the mutual dependency of heat generation and ion diffusion on SOC and temperature respectively. Therefore, they represent a significant increase in accuracy from previous models. The first figure on the left represents a schematic of a single particle model, in which both electrodes are represented by a sphere. The equation underneath the diagram represents spherical diffusion. In this type of model, the concentration and potential in the solution are neglected, and therefore its accuracy is reduced to low C rates. To the right hand side of the single particle model, the figure in the center represents the schematic for a 2D pseudo-thermal electrochemical coupled model. This configuration incorporates the concentration of ions in both the solid and the solution, the potential in both solid and solution, and the kinetics described by the Butler-Volmer equation, as well as its dependency on operating temperature. Similarly to the single particle model, the 2D pseudo model models each electrode as a perfect sphere, and the separator as a linear medium through which lithium ion diffuse during charge and discharge. On the far right hand side, we have more complex models like a 3D model, and a pseudo 2D incorporating the formation in the material as lithium ions intercalate and deintercalate during operation. We also have more complex models like the pseudo 2D model that accounts for different sizes and shapes in the so far assumed perfect sphere particles. Multiphysics thermal electrochemical coupled models characterize important phenomena that takes place during battery operation and that other models cannot capture. We have arrived to the last section. It's time for us to draw some conclusions. One of the first things we learned was that, similar to humans, lithium-ion batteries have a narrow window of temperature comfort. Operating outside this window may reduce battery performance, capacity, and life. At low temperatures, lithium-ion batteries cannot be fully charged. Then, we found out that as the rate of diffusion of lithium ions in the graphite electrode drops during charging at low temperature, lithium starts depositing in the positive electrode. This phenomenon is known as lithium plating, and even though it occurs at low temperatures, it may end up causing thermal runaway. Then, we learned that even though thermal runaway temperatures have been found to be around 300 degrees Celsius, at temperatures as low as 100 degrees, the current collectors start dissolving, damaging the battery. We also found out that at temperatures as low as 80 degrees Celsius, the SEI layer starts to break down, causing irreversible damage to the battery. As we move forward, we also learned that battery performance is highly dependent on temperature conditions. We saw that modeling the rate of heat generation and dissipation in a cell is needed to perform accurate thermal management in battery packs. Last but not least, we can also say that there are different thermal models suitable for different applications and with different computation costs associated with them. I hope you found this tutorial useful and that you enjoyed this material. Thank you very much.